Okay, so maybe you're comfortable with what I'm about to talk about, which is impedance and where it comes from, why it works, and why it's real. Maybe you're already comfortable with this, so you might be bored with how exactly this impedance comes to be. Or maybe you still have questions about how exactly is this real, why is this valid, why does this work the way it does. In which case I'm going to try and come up with an explanation that I sort of came up in a dream one night. So hopefully this makes sense to you guys. I think it works. I think it works great. But tell me if I'm going way too far astray or too crazy, too over your heads. Just let me know. So earlier I talked about sort of a general approach to engineering systems. Like I talked a little bit about, we're working with circuits, voltage, currents, resistors, but there are other kinds of circuits as well. You can have mass spring damper circuits. You can have fluid circuits with reservoirs and water wheels. But you can kind of boil all these down to the lumped element model that the book talks about a little bit in chapter 1, where you have any kind of general one-port element. You can have some variable that's across it and through it. And in our circuits, we just deal with Ohm's law, voltage and current. So over all of our elements, resistors, capacitors, inductors, we have a voltage across this element and a current through it. And for resistors, they're easily related through Ohm's law, V equals IR. But what exactly do we do for inductors and capacitors? We need sort of a V equals IR-like relationship. And if we have that, then we have sort of a general model that we can deal with all sorts of real resistors or capacitors or inductors, for example. So again, we can have current going through all of these elements. We can have voltage differences across all of these elements. But what exactly does that mean? What does that gain us? So if we're looking, again, at during AC steady state, we already know the current to voltage relationship of a capacitor. We've covered this before. So the current is related to the change in voltage, the time derivative of voltage, through the capacitance C. So what happens if we assume AC steady state? So let's say, our solution to the voltage, for example, is a complex exponential, V naught times e to the j omega t plus v. So it's there. What happens if we plug this in to our capacitor relationship? Okay. First, so we plug this in, and we assume that, the current is going to take the same form as the voltage. The voltage is oscillating up and down. You can bet that the current is also going to be oscillating up and down. You can observe this on a scope or anything that you really want. So if we plug in our complex exponential for voltage, and we take the time derivative. So again, for a complex exponential, time derivative, we get a j omega that comes out here. And so we have these complex exponentials. We can see that we have them on each side, so we can cancel them. So this is what leads up to what is a capacitor impedance. We have, it's essentially a resistance is a ratio between voltage and current. So remember the problems we dealt with in the first section of this course where, say you introduce a test source, find what the test current is, and the ratio between the two is a resistance. So that's one example. That's just a voltage over a current that gives you your net resistance. So if we do the same thing for a capacitor, we cancel, again, the exponentials on each side, and we get to see that, sort of what your book takes as, here's what the capacitor impedance is. It's 1 over j omega c. This is where it comes from. So it comes from just taking the AC assumption and plugging it into your CV relations. Your IV relations. So that's how you get, the ratio of voltage over current in this case. It's complex. We still don't know why it's complex or what this J is doing here. But at least we have sort of a basis for what is the impedance. Why is the impedance this? So I assume that that the current is going to take the same form as the voltage. So they're both going to be complex exponentials. So previously we showed in the solutions to the DEs that you plug in sort of a forced response that's an AC wave. Our solution is going to also be an AC wave. So we plugged in that complex exponential to the differential equation. Our solution was also a complex exponential. Yes? Yeah, this could just be, say, a magnitude right here, and now it's being multiplied by an oscillating function. Okay. That's a good question. Are there any other questions? Okay. Oh my God. This is not getting crazy yet, though. So, you guessed it, we can also do the same thing for inductors. Oh my God. So, we start with the same sort of voltage to current relationship for an inductor. And we plug in, again, this time we plug in what the current looks like, and we figure out what the voltage looks like as a result. So again, just taking the time derivatives of the complex exponential and trying to get a voltage to current relationship between from this function, we can define an inductor impedance as well, and just the ratio of voltage to current. So this is how we get the inductor impedance is j omega L. So whereas before the capacitor impedance is like the inverse of j omega, here we see that it's linear. It's directly related to j omega. And that's purely due to this voltage to current relationships and which direction it's defined in. Oh my God. This is getting a little weirder. So in this new context, what about resistors? What happens to resistors? Do we have to rethink how resistors have to operate in AC? Well, no. Don't worry. They stay the same. So it's not much to worry. The first 3 weeks of your course are still valid. You can still rely on them in the future. V equals IR, so it's kind of obvious. V over I is going to equal R. So when dealing with impedances, though, complex values, we'll just use Z across the board. So we've defined Z sub C for a capacitor, Z sub L for an inductor. So we can just say Z for a resistor, Z sub R is some real value to R. And we can see that while the impedance for capacitors and inductors are imaginary, the impedance for a resistor is real. And so it still works within our circuit context that we have real valued resistors, real valued impedances. So they still work out. Yeah? Mm-hmm. Well, because what we're going to see is that this J here, it needs to be there, and it needs to be there for a reason because it doesn't describe necessarily how magnitudes are affected, but it has to deal with the fact that these capacitors and inductors do have time lags and time delays. So I'll get to why exactly we don't take the real part of an impedance just when we're trying to calculate this. So the key thing to remember is impedance is the voltage to current ratio for any passive device. So resistance was just for resistors, but now impedance is for everything. So resistors have a real impedance, and the other great thing about impedances is that they always act like resistors. So what this means is that when we introduced capacitors, for example, capacitors in series don't add like resistors in series. You have to kind of do the backwards parallel operation for them. And capacitors in parallel just add, they don't do what resistors and inductors do in parallel. However, if we replace these L's and C's and R's with their impedance values, then all of them behave like resistors. And so now we can add resistors and capacitors that are in series. We can just add R to 1 over j omega C. And that's our impedance of an R and a C in series, for example. So they start to become easy to deal with. We just now have all these blocks that we can treat just like complex resistors and put things together. So I'm going to have you try this one out just to see if crap. too am unprepared.
Oh man, my battery's almost dead. Node, oh good, it doesn't have the answer on this slide. It's about to give it away.
Okay, so we can find the output voltage of this circuit now. Maybe you'll see where the voltage divider that we went through before comes up. So try and answer, what is the output to input ratio of this circuit? So, you know, now using this sort of impedance method, what is the impedance here? What's the impedance up there? And what is the final expression for the output to input relation? So it requires a bit of a complex arithmetic, maybe a little bit of manipulation, but one of these is definitely right, I promise. Take about another minute, maybe. Yes? Mm-hmm. Yes, that's true. So right now, I haven't done taking the real and imaginary part of this transfer function. So it's still complex. Yeah. So like, this source is Vs e to the j omega t. What is V out going to be in that case? So yeah. And there's value to leaving it like this. As you can see, it's kind of less messy. And we'll see. Yeah, definitely. So I'll go more into the benefits of that and when we do that on Monday. So the question is about why won't we transform these transfer functions into just like a real magnitude factor and a real phase factor. And we'll cover more on when to do that on Monday. But whether you leave it in this complex form or convert it, you still have essentially the same thing. Okay, so it looks like most answers are in here. Does anyone want more time? Okay. 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 All right. So good. Most of you have gotten this right. The answer is E. And we can work this out briefly to... I just want to make sure this sinks in before I zoom along on a bunch of other stuff. So, again, if you just have an RC circuit here. Now, the impedance for the resistor is just R. And the impedance for the capacitor is 1 over j omega c. So now our output to input ratio is a voltage divider. It's going to equal, let's call this Z sub C over the sum impedance, Z sub R plus Z sub C. So I just plug in my values for a capacitor. It's 1 over j omega c. And that's over R plus 1 over j omega c. Okay? And so from here to get into one of the forms like this, I multiply top and bottom by j omega c. So on the numerator, I get 1. And then in the denominator, I get a 1 here. And then I have a j omega c times this R factor. So I have 1 over 1 plus j omega rc, which is E. Does that make sense to anyone who missed it otherwise? Okay. So that's a simple way now of getting a frequency-dependent voltage transfer function. All right, let's try one more now. So this is an LR circuit now, and we can find the output voltage to input current ratio. So try again. What is the transfer function in this case? What is the output voltage to input current ratio? You'll have to do a couple more steps, maybe one or two more steps this time to get to one of these answers. And the right answer is here. Yes. So take a few minutes and try and suss this one out. Okay, I'm going to spook behind the screen for a minute. Okay. How are we doing on responses? Okay. They just keep popping up. Okay, anyone else want a little more time? Take like another 10 seconds, 15 seconds. It looks like everyone's in, I guess. Stop. Yes. Okay, great. All right, that is the right answer. So B is correct in this case. Does anyone want me to go through it? I can go through it. Okay. Okay, well, here essentially the ratio between the voltage and the current is the impedance. So it's just the impedance of the inductor and the resistor in parallel. And so if you do that operation, you'll get the answer B. So I'll say that much, I guess. Okay, so everyone's sort of comfortable with how we work with impedances. That is good. Okay, so at this point, we still don't really know why these impedances are imaginary. And if we add them together, like we did here, we can see that it's not just real or imaginary. These impedances now have a real part and an imaginary part. So, you know, there's sort of a mixture going on, and what exactly does this mean? So, the question still remains. This is what you should be screaming in your head right now. This doesn't make sense. Why does a capacitor have imaginary impedance? What does this mean? And, you know, I've shown you sort of mathematically why it has an imaginary impedance. Maybe that's enough for you. But if you're sort of grounded in what's going on in my circuit and what does J mean in the context of my circuit, I can't measure J on a scope or on a voltmeter. What exactly is going on? Well, so I'm going to try, this is sort of the part where it gets weird. So I think of, we all know that how capacitors store energy. So this is going to be sort of an energy-based argument. Capacitors store energy in an electric field. And we know inductors store energy in a magnetic field. So we know this much about L's and C's. So then what about resistors? What is special about resistors that makes their impedance purely real, while capacitors and inductance have purely imaginary impedances? So let's look at where do resistors store energy. So we know where capacitors and inductors store energy. Where do resistors store energy? They don't. Okay. That's right, they don't. And we know this because we can calculate power loss through a resistor, right? That's the rate of energy the resistor is losing. It's, radiating out every second. So by P equals I squared R or V squared over R, we know that any resistance, any resistor incurs a power loss. And we know that, a power is just an energy rate. So we just multiply by some time or whatever. This translates to an energy loss. The point is that resistors lose power and they lose energy. They sort of, if you have a voltage source, driving a resistor, where's all that energy going? It's being dissipated in the resistor. And if that resistor is like a bulb, maybe it gets converted into light. Maybe it's just a resistor in your lab and it does nothing. So resistors dissipate energy. That's the point. In a circuit, they get rid of energy. So we have one distinction that maybe explains why the impedance of a resistor can be real and the capacitors and the inductors can be imaginary. So maybe you can think of a real impedance as something that really does dissipate energy. It's a real impedance to the system. It gets rid of energy that the source is delivering. And maybe an imaginary impedance is something that, well, it doesn't really dissipate energy. I mean, maybe like it kind of looks like it dissipates energy because you take a voltage source, some of that energy is going into the capacitor. It's going into the inductor. It's not available to the rest of the system to use. So it looks like the capacitor has taken away some energy out of this circuit. But that's not really true because while you can observe voltage drops or changes in current flow, it doesn't result in power loss. That's the point. The energy is still stored in this element. And that's kind of what we're getting at with imaginary impedance. It's not quite real. It doesn't really get rid of power. It stores energy. It stores power. So to get into a little more illustration about this is that, so in AC in particular, we're constantly oscillating. That's the whole point of AC. It's a sine wave. So let's get here. So we have, a voltage difference, let's say, over this capacitor that's changing. One side is positive and negative, then they're equal, and then they start changing, and they go back. And this happens continually. And since we know that the current through this capacitor is due to a change in voltage, then we can sort of plot what happens over a few points. So if we start with one state of a capacitor, let's say the terminals are equal in voltage, so there's no volts, and there's current flowing through it, say charging it. So let's say we have 5 amps, for example. That's just a number I chose arbitrarily. Then after some time, there's a voltage difference across the capacitor. So we go from 0 volts up to 5 volts. And now the current is based on the derivative in the voltage. So up here at 5 volts at max charge, the derivative is 0. So now we have no current flowing through this capacitor. The capacitor is fully charged. Now the cycle changes again, and we have current starting to flow out of the capacitor. As we talked about on Wednesday, this is sort of a charging case, and this is a discharging case. So the capacitor is continually charging and discharging. And what this results in, if we plot the current and the voltage, we see that one waveform lags the other. Okay? And in particular, it lags by 90 degrees. So when we think about J, we can think about J as expressing a lag, a disjoint between the voltage and the current through an element. So it looks like there's impedance here because, I have current here, so I have some difference between current and voltage. I continually have some difference that's changing over time. So it looks like there's some sort of some resistive effect, but it's not. It's really just a phase lag. And so we use the imaginary part, we use J to sort of hang hang on to this sort of effect that's going on. So again, for an inductor, we can sort of see the same thing happen. So here the inductor relationship's backwards. The voltage is due to a di dt. So again, like if we have max voltage, or if we have zero current, this is the point at which current is changing the most. So the voltage is going to be high. And as we go through sort of the cycles in this inductor, we get current flow and then no voltage change. And then sort of the backwards effects start happening. So, you know, we get positive voltage difference and a negative voltage difference, and in between we have current flowing forwards and backwards. Again, that's a charge and discharge-like scenario. But here, because the relationship is inverted, we have now instead the voltage lagging the current waveform. So when we have 1 over j omega c for a capacitor, that means the current is lagging the voltage. Because 1 over j omega c from your complex math, that's just negative j over omega c. So the sign on these plus j, minus j sort of tells us which way the lag is occurring between voltage and current. So impedance then, maybe we can talk about these elements taking power from the other parts of the circuit. So in a way, they do sort of steal power from other places because we need to spend energy charging and discharging these inductors and capacitors. But they're not really getting rid of power, for example. They're storing it. And this sort of charge and discharge behavior results in lags, and lags of different kinds based on whether it's inductive or capacitive. So again, we represent these phase lags with J. All right? So that's why, despite sort of us trying to stay away from complex behavior in a circuit, we use J not to represent some imaginary response, but instead some orthogonal-like response. So instead of, like on the complex plane, instead of having a real impedance, we now have some other kind of impedance. We can represent the difference with it with J and with a phase. So as a summary, for inductors, positive J sign results. And that means the current lags the voltage by 90 degrees or by pi over 2 radians or whatever. And the opposite happens for capacitors. So again, for resistors, they don't have state, they don't have memory, they don't store energy. Nothing sort of lags with resistors. So we have a phase of 0. So there's no J, so it's like a 0 phase change. So voltage and current follow one another. So again, this is sort of the part that gets captured in the phase offset factor. And we'll go into that more Monday, how to calculate it, what it means. But you know, the phase is sort of calculated in this difference between the imaginary impedance of a circuit and the real impedance of a circuit. So it kind of makes sense that this J sort of factors in there. So when you're sort of puzzling over whether this impedance is real or imaginary, try not to think of J as imaginary. It's not the square root of -1 anymore. It's something that's describing a phase effect, another effect. And it's a real effect and you can observe it. We've chosen to use J because like in a complex plane again, we can have real numbers and imaginary numbers. So we can use imaginary numbers to describe different effects from what real numbers describe. So real numbers are described like amplitude effects, or real numbers describe changes in amplitude maybe. J helps us describe other effects. And when you, so when you put these together, you have complex values. And it's just convenient also that by using complex exponentials, we're able to describe the behavior of capacitors and inductors and resistors as well. So it just sort of all comes together nicely by us thinking about J as helping us describe other real effects. There. So that's what I just said. Are there any questions on this? Does this sort of make sense? Does this completely not make sense? Or do you think this is just totally messed up? Nobody? So you're all on the same drugs I am. Cool. Right on. All right. So that's sort of the way I like to think of, if you're struggling with why things are imaginary now all of a sudden, that's sort of an explanation I try to give you. So really, though, we need to abstract away from, what exactly is an inductor and a capacitor. We need to solve real problems with this model. So again, during AC analysis, we now have one general model for what impedance is. And it helps us describe resistors, capacitors, and inductors. So now we can sort of combine all these elements together relatively easily. I mean, sure, complex arithmetic is a pain, but it's less of a pain than trying to solve a differential equation with a cosine waveform. So we can now combine, resistors, capacitors, inductors, and they all act like resistors in the circuit. So you did some examples already, and you can kind of see, okay, they just combine the way resistors do. Now we just have sort of complex values for them. So let's do a few examples. You can sort of see, I'll introduce you to maybe a few a few examples of common combinations. And you'll see that things are a lot easier to describe with resistors than with impedances than say differential equations.
How do you know that the impedances add
So okay, well let's have that be the first example. So if I have two inductors in series, all right, and say this is L1 and L2. So what is the net inductance of this system? It's just the sum, right? L1 plus L2. So now let's look at the impedance version of this. Now I have j omega L1 and j omega L2. All right? So the impedance of this system, the impedance of an inductor is j omega L. So since I know these two inductors are in series and their inductance is L1 plus L2, I know that the impedance of this whole thing should be j omega L1 plus L2 in parentheses. All right? So it should be, the way you can arrive at this using these impedance models, so you just have to add them together. You can factor out the common j omega in L1 and L2 result as your net inductance. So it's compatible with, the existing method of how we think about inductors and capacitors. So the next example, we'll just do two capacitors. Okay, let me draw a little line here. So we have now C1 and C2. So what is the net capacitance of this? You all know. That should be 1 over C1 plus 1 over C2 inverse. Right? Or C1, C2 over C1 plus C2. So now with our impedance model, we have 1 over j omega C1 and 1 over j omega C2. If we add these together, we'll now have 1 over j omega times 1 over C1 plus 1 over C2. Right? Okay. So what is the net capacitance in this case? So let's say we want to get to 1 over j omega C equivalent. All right? So what can we do to sort of bring out this relation? We can just cancel out these 1 over j omegas here. We have sort of our original series relationship, that 1 over C1 plus 1 over C2 equals 1 over C equivalent. Or that we just say C equivalent equals this business inverted. So this is why impedances can just add like normal resistors, because we've already accounted for the way that capacitors and inductors add. That's why we have j omega L for an inductor, so they add together in series. And why it's 1 over j omega C for capacitors, because capacitors add in that inverted manner. The reason why they add in that inverted manner goes back to how is a capacitor constructed. That was part of Monday's talk about the areas adding together versus the separation between the plates adding together. So you can refer to that about why this is the case. So those are two sort of easy examples. Oh, no. Okay, well, I guess I'll do the other on this board. Sorry. So now we can get to things that are a little more interesting. Let's say I had a voltage source. I have a resistor, an inductor, and a capacitor. They all walk into a bar and say, what's the output voltage across the capacitor? Okay. So first, we would start by finding out what's the impedance of the resistor. It's R. What about for an inductor? J omega L. And for a capacitor, it's 1 over j omega C. And now, these are all in series, right? So the net impedance is just the sum of these things. So we have R. That's the real part. Plus J. Now I'm going to do something here. I'm going to say omega L minus 1 over omega C. Okay? Is this clear how I just did this? So, you know, I have... Right, so this converts to negative J over omega C. Just by a virtue of how... Right. Right, so this is 1 over j is like j to the negative 1, and that equals j cubed, which equals negative j. That's the relation I'm using right now. Again, so if this is a little unfamiliar, spend a little time with complex math practicing. So the first thing to note is I have a minus sign in my imaginary impedance. So when could I set this imaginary part to 0? Is this possible? Yeah? They should equal each other. That's right. So when omega L equals 1 over omega C, I get 0. That's kind of neat. So when does that happen? We can say, oh, the frequency omega squared is 1 over LC. This gets into a property called resonance of a circuit, and I'll talk about that more next week. But I drew this backwards, actually, is what I did. Here, we'll do this instead. Put a capacitor here and a resistor here. For the purposes of all I've talked about so far, it shouldn't matter. Okay, so our net impedance is still this, R plus j omega L minus j over omega C. Now, this implies that there's some frequency at which I can minimize the impedance to just R, which is kind of cool. So now let us look at what is going to be the output voltage, V out. How can we express this weird sort of relation? So again, this is a series circuit, so we just need to do a voltage divider. So V out over V in equals. So again, I changed this up a little bit. I'm sorry. It'll make more sense based on what I started talking about. we have a resistor R on the top, and now we have our total impedance on the bottom. Does that make sense to everyone about how how I constructed the voltage divider? Okay. So now we can plug in like real values of L's and C's, and we'll get complex numbers on the bottom. But we have one point at which this goes to 0 under this condition. So in that case, so when omega equals 1 over the square root of LC, I get V out over V in is just R over R, which equals 1. So this is sort of a special property of the circuit that says that at some particular frequency, we can see that these imaginary impedance effects cancel each other out. And so this is probably the best illustration of what an imaginary impedance is, at least in my mind. It means that you have to consider that these aren't real impedances. They're not really losing power. We'll go into more detail on what's going on later, but what this means for you now is that we're not actually losing power here. We can have a direct voltage transfer function that's just 1. We can have this eventually, like they just cancel each other out because of the different ways in which they store and deliver energy to the rest of the circuit. So this is another cool example of how impedances just make that really obvious. You can also figure this out by solving the differential equations as well, but it's kind of a pain. That's sort of the point. Okay. Yes? So, negative impedance or resistance? Which one do you want to go with first? Okay, so the important thing to note about impedances, at least in the context of this kind of circuit, we have a resistance R. So the real part is R. Generally, that's always positive. All right. Then the imaginary part we call the reactance. So normally we would write this as R plus JX. And X is called the reactance. So positive reactance means the circuit behaves inductively. And a negative means the circuit behaves capacitively. Oh. Yeah. All right. So what that means is just a type of in what manner is the energy being stored? Yeah. Yes? So at resonance, what happens? Yes. So yes, there is a voltage difference. Oh, what happens at resonance is that you have some voltage difference across this capacitor, and you get the exact opposite voltage difference across the inductor. So that is how they end up canceling each other out. Okay, good question so far. Are there any other questions? These are all pretty important to ask now, so more questions. Awesome. Okay. So this is the previous circuit that we had that was like kind of hairy, kind of crazy. But now with impedances, just want to walk you through one example in how we can combine resistors and capacitors, and that's all I have. So the impedance for the resistor R we know is R1. And I'm not going to ask you guys what's the impedance for each one because you seem to be on top of that already. So for this first capacitor, we have 1 over j omega C1. R2 is the impedance for the second resistor. 1 over j omega C2 is the impedance for the second capacitor. So now we've translated these resistors and capacitors into impedances. I've drawn boxes here because now we're dealing with sort of complex valued boxes of impedances. You can still draw the resistors and capacitors if you want, but the thing is now we're generalizing. We're abstracting away from the physical basis of these values. Now we're saying, okay, you know, we've shown how resistors are R, capacitors are 1 over j omega c, inductors are j omega L, so like we're cool with that now, and we're going to just abstract away from that. So now, again, how do we combine these two elements? You guys know these two boxes are in series, so their impedances just add in series, right? So that's what we get. Now these two are in parallel, and it's true the math gets a little hairy, but you can just do the parallel operation on these two elements. And now it's fairly obvious that what we have here is just a voltage divider between these two. So I'll leave it to you to do the math on what exactly is the final answer. But it's going to be a little bit more complicated than just an R and a C, but you'll see in the end that it has some RC factor, and it has a bunch of other sort of familiar things that we'll be investigating more on Monday. Yeah? Yeah, you can do it that way as well. It's really just a style thing. So I leave them like this. In the event that for me, it's like easier to just multiply R1 and 1 over j omega c when I know instantly, oh, it's just a ratio. So that's what I did here, is like when I multiplied, just put them like that. It's totally up to you, whatever works. Yeah? Yes, that's a very good point. That's a great question, because it brings up the important fact that when omega is 0, your frequency is 0, you're at DC, and at DC, the impedance of a capacitor goes to infinity. And the impedance, an infinite impedance is an open circuit. So that's a very important, that's a very good point and a good question. So conversely, we have the impedance of an inductor is j omega L. So that implies at a DC value of 0 hertz, when omega is 0, the impedance of an inductor is 0. It's just a wire at that point. It's a short circuit. And so this perfectly matches with the steady state analysis that we did on Wednesday and on Monday.